Welcome to our lecture on non-chordates. Today, we are going to explore one of the most bizarre and fascinating developmental processes in the entire animal kingdom. Imagine carrying a heavy backpack, and suddenly your entire torso twists around so that your backpack is resting directly over your head. This dramatic biological gymnastics routine is a real phenomenon called torsion, and it happens to snails and slugs. Let us dive in and understand how and why this happens. Now that we have a visual idea of this bizarre twist, let us look at how it begins. During its early life, a baby snail, known as a veliger larva, looks quite normal. Its mouth is at the front, and its waste exit is at the back. But as it grows, a dramatic 180-degree body twist occurs. Its internal organs, shell, and even its nerve cords twist around, bringing the rear end right above its head. This is not an accident, but a highly choreographed developmental stage. Building on that intuitive picture, let us define this process formally. In zoological terms, torsion is defined as the 180-degree counterclockwise rotation of the visceral mass, mantle, and shell with respect to the head and foot of the gastropod. This remarkable rotation happens specifically during the free-swimming veliger larval stage. Because of this counterclockwise twist, the mantle cavity, which houses the gills and the excretory and reproductive openings, is brought all the way to the front of the body, positioned just behind the head. This massive rotation does not just move the shell, it completely reorganizes the internal anatomy. As the mantle cavity moves forward, the digestive tract is forced to bend into a U shape. Even more fascinating is what happens to the nervous system. The nerve cords are physically twisted into a figure-8 pattern. In the scientific community, this crossed nerve condition is known as streptonury. It is a permanent anatomical record of the twisting process that the larva underwent, proving just how profound this developmental change really is. You might be wondering, why on earth would an animal evolve to twist its body so drastically that it empties its waste on its own head? The primary evolutionary advantage of torsion is protection. The head of the snail is highly sensitive and vulnerable. Before torsion, if a predator attacked, the foot would retract first, leaving the head exposed. After torsion, the mantle cavity is at the front. This allows the snail to pull its delicate head into the safety of the shell first, followed by the tough foot, which acts like a protective door. Beyond just physical protection, this twist offers massive survival benefits for the snail's daily life. By bringing the gills to the front, the snail can breathe clean, oxygen-rich water as it moves forward. If the gills were at the back, they would draw in muddy water stirred up by the snail's own crawling. Additionally, the sensory organs, called osphragma, are brought to the front. These act like a chemical radar, allowing the snail to test the water ahead for food or dangerous toxins before moving into a new area. To truly understand this anatomical shift, let us look at a detailed diagram of the torsion process. On the left, you see the anatomy before torsion, with the mouth at the front and the anus at the back. Notice the straight nerve cords. Now, follow the large circular arrow indicating the 180-degree counterclockwise rotation. On the right, after torsion, the anatomy is completely transformed. The anus is now positioned above the head, and you can clearly see the streptonury, where the nerve cords have crossed into a figure-8 shape. While torsion is a biological marvel, we can actually understand its mechanics using basic physics and kinematics. The rotation happens in two distinct phases: a rapid phase driven by muscle contraction and a slower phase driven by uneven cell growth. We model this with the formula theta equals omega-1 times T1 plus omega-2 times T2. Here, theta is the total angular displacement of 180 degrees. Omega-1 and T1 represent the angular velocity and time of the rapid muscle phase. Omega-2 and T2 represent the slower tissue growth phase. If the muscle contraction speed increases, the time required for the first half of the twist decreases, protecting the snail faster. Let us see this formula in action with a real biological example. A marine biologist observes a larva undergoing a total rotation of 180 degrees. The first 90 degrees happen rapidly at 30 degrees per hour. The remaining 90 degrees happen slowly at 5 degrees per hour. We need to find the total time. First, we divide the 90 degrees by 30 degrees per hour, giving us 3 hours for the rapid phase. Next, we divide the remaining 90 degrees by 5 degrees per hour, giving us 18 hours for the slow phase. Adding these together, the final answer is 21 hours. This means the vulnerable larva spends nearly a full day transforming. Now that we have used the formula to find the total time, let us understand the algebraic reasoning behind those calculations. We started with the fundamental kinematic principle that angular displacement equals angular velocity multiplied by time. To find the time for the first phase, we must isolate the variable t1. By dividing both sides of the equation by the angular velocity omega-1, we get t1 equals theta-1 divided by omega-1. This simple algebraic rearrangement is crucial because it allows biologists to predict developmental timelines based purely on observed rotational speeds under a microscope. Continuing our derivation, we apply the exact same mathematical logic to the second phase of torsion. We isolate T2 by dividing the angular displacement theta2 by the slower angular velocity omega-2. Finally, to find the total developmental time, which we call T sub r, we simply add the time of the first phase and the time of the second phase together. This gives us the final derived equation. Total time equals theta-1 over omega-1 plus theta-2 over omega-2. This proves exactly how the individual biological rates sum up to dictate the snail's overall transformation period. Evolution is full of surprises, and millions of years later, some gastropods decided to reverse this entire process. This evolutionary reversal is called detorsion. It is primarily seen in advanced gastropods, such as a lineage of sea slugs known as opistobranchs. During their development, these sea slugs partially or completely untwist their bodies back to the original straight alignment. By regaining this bilateral symmetry, the sea slug develops a highly streamlined shape, which is absolutely perfect for gliding smoothly and actively swimming through the ocean currents. Just as we modeled the initial twisting, we can also measure the speed of this evolutionary untwisting process. We use the standard kinematic formula rearranged to solve for velocity. Omega sub d equals theta sub d divided by t sub d. In this equation, omega sub d represents the angular velocity of detorsion. Theta sub d is the total angle of untwisting, and t sub d is the total time it takes to complete. The subscript d specifically denotes that these variables apply to the detorsion phase. This simple division gives us a perfect way to quantify exactly how fast the animal is altering its body plan. Let us apply this rate formula to a specific sea slug larva observed by a marine biologist. We are given that the larva undergoes a partial detorsion of 90 degrees. We are also told that this untwisting process takes exactly 45 hours of steady cell growth. We need to find the angular velocity. By plugging our values into the formula, we divide the 90 degrees of displacement by the 45 hours of time. The mathematical result is exactly 2 degrees per hour. This extremely slow rate indicates that detorsion is a gradual, deliberate developmental change, allowing the slug to safely regain its symmetry. We have covered a fascinating journey of biological adaptation today. Remember that torsion is a dramatic 180-degree twist that protects the snail's head and optimizes its senses. We also learned that this biological event can be precisely modeled using kinematic physics, breaking it down into rapid and slow phases. Finally, we saw how detorsion acts as an evolutionary reversal, allowing sea slugs to untwist and become streamlined swimmers. You now have a complete understanding of this incredible biological phenomenon.